recording. Okay. Uh, this lecture, um, let me add a student. This lecture introduced the topic of transient in power system with a particular focus on uh, traveling waves in transmission and distribution networks. Let me add a new student. Okay, transient or short duration disturbances that occur in electrical power system due to sudden changes such as switching operations or fault or lighting strikes or load variation and so on. So these disturbances propagate along transmission lines in the form of traveling waves, which can significantly affect system voltage and current behavior. And understanding traveling waves is very essential for analyzing um, over-voltage conditions, insulation coordinations, and protection of the power system equipment in general. So, in this part of module, the fundamental concepts of transient phenomena will be developed to help you better understand how electrical disturbances propagate and how they can be controlled and mitigated in modern power systems. Okay, this slide present the main contents covered in the topic of transient in power systems and traveling waves. The lecture will be begin with an introduction to the basic concept of transient phenomena in transmission lines, followed by the study of the transmission coefficient, which describes how incidence waves are reflected and transmitted at discontinuous, and it then examines different types of transmission line terminations and their impact on wave behavior, including open circuit, short circuit, and match conditions. The concept of wave velocity is also introduced to explain how fast electrical disturbances propagate along the line depending on its physical and electrical properties. And at the end, eventually, the lattice diagram will be discussed as a symmetric analytical tool used to track multiple reflections and refractions of traveling waves over time. And this structure overview provides a clear roadmap for understanding wave propagation in power systems. Okay, this slide introduces the basic concept of voltage transients in power systems. A sudden and short duration rise in voltage within the system is referred to as a voltage surge or transient voltage. These transients are important because they can stress insulation and damage electrical equipment if not properly controlled. And the causes of over voltages in power systems are generally classified into two main categories. Let me add a new student. Uh, The first category includes internal causes such as switching operations, insulation failures, and resonance conditions within the network. And the second category consists of external causes, with lightning strikes being the most significant sources. And understanding these origins is very essential for analyzing transient behavior and designing appropriate protection measures in power transmission and distribution systems. Okay, this slide introduces the concept of transmission coefficient in the context of traveling waves on transmission lines. It begins by referring to the characteristics impedance of the line, which is a fundamental parameter describing the relationship between the voltage and current for a wave propagating along an infinite or lossless transmission lines. Sorry. The characteristics impedance plays a key role in determining how an incident wave behaves when it encounters a discontinuity of or a change in impedance. The transmission coefficient is then used to quantify the portion of the incident wave that is successfully transmitted into the next section of the line as opposed to being reflected back. So this concept is essential for analyzing wave propagation, impedance matching, and transient performance in power transmission systems. Okay, this slide explains the practical simplification used in evaluating the characteristics impedance of transmission lines and cables. So since the resistance R and conductance G of overhead lines and underground cables are generally very small compared to their inductance L and capacitance C, they can be neglected for transient analysis. So under this assumption, the characteristics impedance simplifies to Z0 is equal to a square of L over C, which provides a more practical and widely used expression for wave propagation studies. So the slide also highlights typical values of characteristics impedance in real systems. For overhead transmission lines, is typically ranges from about 200 to 700 ohm, while for underground cables it is much lower, typically between 20 and 80 ohm. This significant difference is mainly due to the higher capacitance of cables compared to over lines, which strongly influences their transient behavior and wave propagation characteristics. Okay, this slide illustrates a wave propagation problem in a branch transmission line network where the positive direction of the wave travel is defined from left to right. An incident wave with velocity v travels along line 1 with characteristic impedance Z1 until it reaches a junction. At this branching point, the wave energy is divided into two outgoing paths, line 2 with impedance Z2 and line 3 with impedance Z3. The diagram highlights how impedance differences at the junction influence the transmission and reflection of waves. So this type of configuration is commonly analyzed in power systems, signal transmission and electromagnetic waveguides to understand how waves behave when encountering network disconnections. Okay, this slide explains the relationship between the traveling voltage wave and corresponding current in the transmission line system. For the incident wave with amplitude V, the associated current is determined by the characteristic impedance of line L given by I is equal to V over Z1. When the wave reaches the junction, part of the wave is reflected back along line 1, represented by VR. So while the remaining portion is transmitted into connected branches, represented by VT. So each of these voltage components produces its own associated current according to the impedance of path through the which it travels. So this formulation is essential for applying continuity conditions of voltage and current at the junction, which are used to calculate the reflected and transmitted wave magnitudes. So this slide derives the currents associated with the reflected and transmitted voltage waves at the junction of the branch transmission line. The reflected wave current is expressed by as IR is equal to minus VR divided by Z1, where the negative sign indicates that the reflected current travels in the opposite direction to the defined positive wave direction. So the transmitted current is given by IT is equal to VT over Z equal, where Z equal is the equivalent terminating impedance seen at the end of line 1. So since lines 2 and 3 are connected in parallel at the junction, their combined impedance can be calculated based on this equivalent impedance. So this equivalent impedance simplifies the network analysis and allows the branching junction to be treated as a single load when determining wave reflection and transmission behavior. Okay, this slide also is showing the application of fundamental circuit laws, especially Kirchhoff voltage law and Kirchhoff current law, to analyze the continuity of the system. By examining the loop shown in the diagram, KVL is applied to relate the voltages across different elements, leading to the expression V plus VR is equal to VT, which indicates that the total voltage is the sum of the individual voltage drops. At the same time, KCL is used at the node level to ensure current continuity, resulting in I plus IR is equal to IAT, meaning the total current is the sum of the branch current. Together, these equations confirm that both energy and charge are conserved within the system, forming the basis for accurate circuit modeling and analysis. Okay, this slide extends the previous analysis by expressing the circuit relationships in terms of impedances and currents, starting from Ohm's law in the phasor domain. So we have this Ohm law. The current through impedance Z1 is given by I is equal to V over Z1, while the reflected or opposite current is defined by as IR is equal to minus VR over Z1, where the negative sign indicates the opposite direction of flow. So on the right hand side of the network, the total current following into the equivalent impedance expressed by IAT is equal to VT divided by Z equal. So by applying current continuity at the junction, these expressions are combined to obtain this equation. So these equations provide a key relationship between incident, reflected, and transmitted equations, forming the foundation for analyzing wave propagation and impedance matching in the systems. So this slide derives the expression for the reflected voltage by substituting the previously obtained relationship Vt is equal to V plus Vr into the current equation. As a result, the reflected voltage is expressed as this one because just we need to substitute all of equations together, so which can be completely written as Vr is equal to KRV. So where Kr is defined as a reflection coefficient, the reflection coefficient given by this equation, Z equal minus Z1 over Z equal plus Z1. So The quantities, how much of the incident voltage is reflected due to the impedance mismatch between Z1 and equivalent impedance, EQ. So the slide also highlight that Kr lies within the range -1 and 1, indicating that the reflected wave can vary from destructive reflection to constructive reflection depending on the impedance conditions. Uh, Let me add a new student. Um, this concept is fundamental in transmission line theory and plays a critical role in ensuring efficient power transfer and minimizing signal reflections. Okay, this slide introduces Kr as a reflection factor, emphasizing its physical meaning in wave propagation, especially Kr represent the ratio of the reflected reverse traveling wave to the incidence forward traveling wave. So in other words, it quantifies how much of the original signal is sent back due to the impedance discontinues in the systems. A value of Kr is equal to 0 indicates perfect impedance matching with no reflection, while values close to -1 um, uh, ±1 indicate strong reflection either in phase or out of phase. So this interpretation is essential for understanding signal behavior in transmission line, where minimizing the reflection factor is critical for efficient power transfer and system stability. So this slide explains how the transmitted voltage wave behaves when a traveling wave encounters a junction between transmission lines. The total transmitted voltage Vt is expressed as the sum of the incident voltage V and the reflected voltage Vr, which leads to the relation Vt is equal to V plus Vr. Uh, by factoring this becomes this one. Just by factoring Kr, we can find this equation where Kr is the reflection coefficient, as I told you before. So this allows us to define a new parameter, the transmission coefficient Kt, such that Vt is equal to Ktv. This slide further drives KT in terms of impedances, showing that it depends on the equivalent impedance that they equal and the line impedance that they one. The final expression KT is equal to 2ZA equal divided by ZA1 plus ZA equal. So highlights that the amount of transmitted voltage is strongly influenced by impedance matching. This concept is essential in understanding wave propagation and minimizing losses or reflections in transmission systems. So this slide present the behavior of the current wave at the junction of transmission lines, complementing the voltage analysis from the previous slide. So the reflected current IR is expressed in terms of the incident current I and the impedances leading to the relation IR. So this can also be written as IR minus KRI, showing that the reflection coefficient for current has the same magnitude as for voltage but with an opposite sign, so indicating a phase reversal. The transmitted current IT is then obtained by summing the incident and reflected currents, giving IT is equal to IR plus I. Substituting the expression for IR, we arrive at IT is equal to this equation. So this allows us to define the current transmission coefficient K prime, where IT is equal to K prime times I, and K prime can be calculated based on this equation. And in overall, this slide highlights how current transmission depends on impedance relationships and emphasizes that unlike voltage, the reflected current undergoes a sign change. This distinction is crucial for accurately analyzing wave propagation and power flow in transmission systems. Okay, this slide emphasizes a fundamental relationship between voltage and current waves in transmission line analysis. So it states that the current wave can always be determined by dividing the corresponding voltage wave by the surge impedance of the transmission path. In other words, for any traveling wave, the ratio of voltage to current is not arbitrary but fixed by the characteristic or surge impedance of the line. So this means that once the voltage waveform is known, the current waveform can be directly obtained by using of this. This is a Ohm law, very simple equation where Z1 represents the surge impedance of the medium through which the wave is propagating. So this principle is essential because it simplifies the analysis of wave propagation, reflections, and transmissions by allowing you to move easily between voltage and current representations while maintaining consistency with the physical properties of the transmission lines. Okay, this slide provides a complex summary of the key equations governing both voltage and current reflections and transmissions at a transmission line junction. For the voltage waves, the reflected component VR is expressed as a function of the impedance mismatch between Z1 and Z equal, while the transmitted voltage VT depends on how how much of the incident wave passes through the boundary. Similarly, for the current waves, the reflected current IR follows comparable uh, form but with an opposite sign behavior relative to voltage, and the transmitted current IT is determined by the proportion of current that continues into the next operation of the system. So these expressions clearly show that both voltages and current distributions are fully controlled by the ratio of impedances. When the impedances are matched, reflections vanish and maximum transmissions will be occur. So on the other hand, any mismatch leads to partial reflection and reduced transmission. So this set of equations is fundamental for analyzing traveling waves, showing efficient energy transfer, and designing transmission systems with minimal losses and disturbances. Okay, this slide introduces the different possible terminations of the transmission line when a traveling wave reaches its end, which is a critical factor in determining how the wave behaves. So when a step or pulse arrives at a remote end, the line can be terminated in three main waves: an open circuit, a short circuit, or a lump resistance. So in the case of an open circuit line, no current can follow, so the wave is fully reflected with the same polarity, resulting in a reflection coefficient of +1 for voltage. For a short circuit line, the voltage at the end must be zero, so the wave is totally reflected, but with reverse polarity, giving a reflection coefficient of -1. Let me add a new student. Okay, the third case, a lump resistance termination, represent a more general and practical scenario where a part of the wave is observed and part is reflected. If the resistance matches the surge impedance of the line, reflections are eliminated entirely and achieving a perfect transmission. So, overall, this slide highlights how termination conditions directly influence reflections, making them crucial in the design and protection of transmission systems. Okay, this slide explains the behavior of open circuit transmission line, where the receiving end impedance is infinite, so Z2 is equal to infinite, meaning no current can follow at the end of at the load end. So as a result, the entire incident wave is reflected back toward the source. So the reflected voltage VR is equal in magnitude and phase to the incident voltage V, leading to a voltage doubling effect at the sending end where Vt is equal to 2V. On the other hand, the reflected current IR is equal in magnitude but opposite in direction to the incident current I, which results in zero total current at the open end. IT is equal to zero. The reflection coefficients further confirm this behavior. The voltage reflection coefficient Kr is equal to 1 indicates full reflection without phase change, while the current reflection coefficient Ki is equal to -1 indicates a complete reflection with inversion. So consequently, the transmission coefficient for current Kt is equal to 0 and reflects the fact that no current is transmitted behind the open circuit. So this scenario highlights how open circuit conditions lead to maximum voltage buildup and zero current at the termination points. Okay, this slide describes the behavior of a transmission line under short circuit conditions where the load impedance is zero. In this case, the voltage at the receiving end must be zero since a short circuit cannot sustain any voltage difference. So consequently, the incident voltage wave is completely reflected with phase reversal, resulting in a reflected voltage VR is equal to -V, and a total voltage at the load of Vt is equal to zero. In contrast, the current behavior is different. The reflected current IR is equal in magnitude and in phase with the incident current I, you can see here, leading to a doubling of current at the receiving end. On the other hand, IT is equal to 2I. The reflection coefficients support this interpretation, where the voltage reflection coefficient R is equal to -1 indicates total reflection with phase inversion, while the current transmission coefficient Kt is equal to 2. Shows that the current at the load is twice the incident value. So this scenario illustrates that a short circuit line results in zero voltage but maximum current at the termination point, which is critical in understanding fault conditions in power systems. So this slide present the case of a transmission line terminated with a lump resistance R, which represent a more general and practical condition compared to open and short circuit cases. Here, the load impedance Z2 is equal to R is finite, so part of the incident wave is transmitted into the load while the rest is reflected back along the line. So the voltage reflection coefficient is given by Kr. R is equal to this equation, R minus Z1 over R plus Z1, showing that the magnitude and phase of the reflected wave depend on the mismatch between the line characteristic impedance Z1 and the load resistance R. So when R is equal to Z1, the reflection coefficient becomes zero indicating perfect matching and no reflection. So the transmission coefficient for voltage is equal to um, 2R over R plus Z1, which determines how much of the incident voltage reaches the load. So similarly, the current transmission coefficient is equal to K prime T is equal to 2 Z1 over R plus Z1, reflecting how current is distributed at the termination. These expressions demonstrate that by properly selecting the load resistance, reflections can be minimized or eliminated, which is a key principle in transmission line design for efficient power transfer and signal integrity. Okay, this slide integrates the concept of wave velocity in transmission systems, which is a fundamental parameter in understanding how electrical signals propagate along a line. So the velocity of propagation depends on the excuse me inductance L and capacitance C per unit length of the transmission medium. So mathematically, it is expressed as V velocity is equal to 1 over square LC. This equation shows that the wave velocity is inversely proportional to the square root of the product of inductance and capacitance. Physically, higher inductance or capacitance shows down the propagation of the wave, while lower values allow signals to travel faster. In practical power systems and communication cables, this relationship helps you design lines with desired signal speeds and minimal distortion. So understanding wave velocity is especially important in high frequency applications and long transmission lines where signal delay and wave behavior significantly impact system performance. Okay, this slide introduces the lattice diagram. So a powerful graphical tool used in the analysis of traveling waves on transmission lines and cables. Lattice diagram provides a step-by-step visual representation of how voltage waves propagate, reflect, and transmit along a line over time can be modeled. So instead of solving complex equations repeatedly, you can use this method to track wave interactions at different points, such as junctions, terminations, or impedance changes. So in essence, the lattice diagram maps the movement of incident and reflected waves along the line using a grid-like structure where each line represents a wave traveling in a specific direction. So by following the path within the diagram, it becomes much easier to calculate the voltage at any location at any instant in time. This method is especially useful in transient analysis where sudden changes like switching operations or faults cause multiple reflections. So overall, the lattice diagram simplifies the understanding of wave behavior and helps you accurately predict voltage variations in complex transmission systems as well. Let me check. Yes, we have one student. Okay, this is like explain example one, which focus on analyzing a transient over voltages in a transmission system using traveling wave theory. So the problem considers a transmission line of 46 kilometer with given inductance and capacitance values. So, and an initial rectangular voltage wave of 110 kilovolt that starts propagating from busbar 1 toward busbar 2 at time 0. So the goal is to determine how these waves evolve over time and to calculate the total over voltages accumulated at each bus bar over after 500 microseconds. So a key step in solving this problem is determining the wave velocity along the line, which depends on the distributed inductance and capacitance. Uh, so velocity is equal to 1 over, we have this equation, 1 over square 3 square root of LC. So using this velocity, we can calculate the travel time of the wave between the two bus bars and track how many reflections occur within the 500 microsecond interval. So the presence of the shunt resistor at busbar 2 introduces partial reflection and transmission of the wave. So meaning that each time the wave reaches this point, part of it is observed while the rest is reflected back toward busbar 1. So similarly, reflections may also occur at the sending end depending on the boundary conditions. So by applying the lattice diagram method, so introduced in the previous slides, we can systematically follow each incidence and reflected wave, summing their contributions at both bus bars. So this allows us to determine the cumulative overvoltage at each location. And in overall, this example will demonstrate how transmission line parameters, termination conditions, and wave interactions combine to influence transient voltage behavior in power system. Okay, this slide present the fundamental parameter calculations for a transmission line using its inductance and capacitance values. First, the inductance L is equal to 1.53 times 10 power minus 3 Henry, and capacitance C is equal to 17 times 10 power minus 9 uh, Farad. So forming the basic for further analysis. So using these parameters, the the characteristics impedance of the line can be calculated as ZC is equal to square root of L over 3 over C is equal to the 300 ohm, which represent the inherent opposition of the line to traveling waves. Next, the propagation velocity can be determined by using of this equation, so indicating how fast signals travel along the line. So based on this velocity, the time delay tau is equal over a distance of 46 meters is computed as this value, microsecond. So which is then defined as a theta. Theta is equal to tau 1. So finally, the ratio of given time 500 microsecond to this delay is calculated as tau t, providing insight into how many propagation intervals fit within the specified time. So overall, the slide systematically demonstrate how basic line parameters can be used to derive key transmission characteristics such as impedance, velocity, and time delay. Okay, this slide focuses on the reflection characteristics of a transmission line terminated with a shunt resistor. So the shunt resistance is given as R shunt is equal to 150.6 ohm, and it plays a key role in determining how signals reflect at the receiving end. So at the sending end, the reflection coefficient is calculated as CoRS is equal to, so this is a sending end, so 0 minus 300 divided by 0 plus 300 is equal to minus 1. So indicating that a reflection with polarity inversion, which typically correspond to a short circuit condition as we discussed before. So at the receiving end, the reflection coefficient can be equal to this one. So it's equal to minus 0.332, showing a partial reflection due to impedance mismatch between the line characteristic impedance and the shunt resistor. So the diagram below illustrates the system configuration where the transmission line connects bus 1 and bus 2 with a shunt resistor connected to a ground here, um, um, and at the receiving end. So this setup helps visualize how reflections occur at both ends of the line and highlights the impact of termination impedance on wave behavior. So this slide is showing the traveling wave behavior along the transmission line and how multiple reflections influence the voltage profile at both ends. So starting from bus 1, an initial wave incidence wave of 1 per unit here um, propagates toward bus 2. This is 1 per unit. So when the wave reaches the receiving end, part of it is reflected back due to the reflection coefficient. CR is equal to minus 0.3316, generating a negative wave reflected wave the sending end. So no, we can come back here. This reflect wave then reaches bus 1 where it undergoes another reflection with the coefficient Kr is equal to minus 1, producing a mode with wave with magnitude 0. Plus 0.303 3316 traveling to the end of the uh, receiving end, bus 2. So this diagram visually tracks these forward and backward waves over time, showing how their magnitude diminish due to partial reflections by uh, superimposing these waves, resulting voltages at both buses can be calculated. At bus 1, the total voltage becomes V1 is equal to 1 minus 0.3316 plus this one times 110 is equal to 110 kilovolt, meaning the reflection cancel out and restore the original voltage. At bus 2, V2 will be equal to this one. So indicating a reduced voltage due to incomplete transmission and reflection losses. So in overall, let me add a new student. Okay. In overall, this slide demonstrates how traveling wave reflections and transmission coefficient interact to determine the transient voltage distribution along the line. Okay, this is another example, present a practical example of transient analysis in transmission systems, focusing on the calculation of total over voltages at different bus bars. So I will give you 10 minutes off and come back again to the discussion. Let me just give me a second.